In our last lesson, we saw that we could tell how many valence electrons an atom has by its position on the periodic table. When a property varies based on its position on the periodic table, we call that a periodic trend. And in this lesson, we're going to take a look at two other periodic trends. We're going to look at atomic size, that is how big an atom is, and ionization energy, which is how much energy it takes to pull an electron off an atom. Let's take a look at these two periodic trends. One simple example would be atomic number. So remember that the little number up here represents the number of protons. And what you can see is as we move from left to right on the periodic table, the atomic number increases. So boron's 5, carbon 6, nitrogen 7. Or as we go from top to bottom, the atomic number increases. So we have 7 for nitrogen, 15 for phosphorus, and 33 for arsenic. So that's one property that varies as we go across the periodic table. Another one that we'll talk about in this video is atomic size. So for example, let's look at fluorine, chlorine, bromine, and iodine and think about how big they are. If we draw out their sizes, we'll see that if I make F2, this should be just F2, it will be 128 picometers from nuclei to nuclei. Chlorine is 200 picometers. Bromine is 228 and iodine is 266. So what's happening is these atoms are getting bigger and bigger as we go down the periodic table. And that's the trend of atomic size. There's two different things to think about here. One is as we go from top to bottom, the atomic size increases. That's not so surprising. So that means that oxygen, for example, is smaller than polonium. This makes sense because as we go down the periodic table, we're adding more and more electrons into bigger and bigger orbitals around the atom. So that one's pretty easy to understand. Atomic size also turns out to increase as we go from right to left. So that means, for example, that fluorine is smaller than boron. So fluorine's smaller than boron. That one's a little harder to explain. The reason this turns out to be is that we're adding more we're adding more protons to the nuclei, and that makes the charge of our nucleus bigger and bigger. At the same time, our electrons aren't getting any farther away because as we move left to right on a given row, we're just adding more electrons into the same orbital. And so those get sucked closer and closer. So if you don't understand the explanation, that's okay, but make sure you know that atomic size increases as we go down the periodic table and as we go right to left. Let's talk about one other property and its trend before we work some problems. Ionization energy is another important property, and what it tells us about is how hard it is to remove an electron. So it's very specifically the amount of energy needed to remove an electron. So if I imagine a neutral atom here, which has a blue nucleus and 6 electrons, how much energy does it take it to get to this positively charged atom where one of my electrons is shooting off? So, right, that would make this whole thing positively charged. So I've removed an electron. I've ionized it. An ion is something with a charge, and I've just made it an ion. So I've ionized it. I've removed that electron. How hard is that? Well, it turns out that we can predict how hard that's going to be, at least relatively speaking, by its position on the periodic table. For ionization energy, we can see that it gets harder to remove an electron as we go up. It also gets harder to remove an electron as we go to the right. Why is that? Well, let's say we look at hydrogen and we compare it to lithium. Hydrogen has 1 electron and it's pretty close to its nucleus because hydrogen is small. And because hydrogen is so small, if I try to pull off that electron, it takes more energy than it does for lithium. Because lithium's electron that I would remove is actually farther away from the nucleus. So that means the energy needed to remove an electron increases as I go up. Ionization energy also increases as I go to the right for the same exact reason that the atomic size varied left to right. As the atoms get smaller as I go left to right, that makes their electrons closer to their positively charged nucleus and hence harder to remove. So remember that for ionization energy, it gets harder to remove an electron as I go up the periodic table or as I go to the right on the periodic table. Let's work some practice problems, first with size. Okay, this question says determine which of the following has larger atomic size from the periodic trend. Okay, so we're thinking here about atomic size, and I have our periodic table and our trend. First, we're going to compare hydrogen, which is right here, to helium. Well, our atomic size trend tells us that our atom gets bigger as we go to the left on the periodic table. Hydrogen is more to the left, so that makes hydrogen bigger. If we compare chlorine and fluorine, chlorine is below fluorine. It has more electrons, it's bigger, because remember our atomic size trend tells us it increases as we go down. So we get chlorine that's bigger. Okay, the next comparison is going to be aluminum and silicon. So once again, let's locate them on the periodic table. Here's aluminum and silicon. Aluminum is to the left of silicon. And remember, as we go to the left, things get bigger. So we know aluminum's bigger. Oxygen or sulfur. Oxygen and sulfur are stacked right on top of each other. Sulfur is lower on the periodic table, and that makes it bigger. Okay, now we get to a slightly more interesting one. We're going to compare nitrogen and silicon. So here's nitrogen, and here's silicon. Well, silicon is to the left of nitrogen, so that suggests it's bigger. Silicon is also below nitrogen, so that suggests it's bigger. So that one's pretty straightforward. Silicon is bigger. And now for the most interesting one of all, carbon compared to phosphorus. Carbon is right here, and phosphorus is right here. And this one is trickier, because as we go to the left, we would suggest from our trend that carbon would be bigger than phosphorus. However, as we go down, our trend would suggest that phosphorus was bigger. So here we have competing suggestions for which one's bigger from our two trends. And that means it's totally okay to just say that you can't tell. That is the totally acceptable answer for our periodic trends. So can't tell is an option that sometimes happens, and it happens when going down suggests one thing and going left or right suggests the other. Okay, so that's for atomic size. Let's take a look now at those same comparisons for ionization energy. Once again, we're going to start with hydrogen and helium. Ionization energy has the opposite trend of atomic size. And so that means all of our answers, frankly, are going to be opposite. Helium is more to the right, so it's bigger. Sorry, not bigger. It has a higher ionization energy. Chlorine and fluorine, those are stacked on top of each other. As we go up on the periodic table, we get higher ionization energy, so fluorine is going to have a higher ionization energy. Aluminum or silicon are right here, and silicon is to the right of aluminum, and so that means it's going to have a higher ionization energy. We have oxygen and sulfur right here. Sulfur is below oxygen, so that means oxygen's higher up, and hence has the higher ionization energy. Okay, now we're to our more interesting comparisons here. We're going to compare nitrogen and silicon. So nitrogen's here, silicon's there. Well, as I go to the right, I see that nitrogen is to the right of silicon, so that suggests it has a higher ionization energy. As I go up, nitrogen is above silicon. So both of those suggest that nitrogen has my higher ionization energy, and it does. Carbon versus phosphorus, once again, has the same issue. There's carbon, there's phosphorus. As I go to the right, I see that phosphorus is to the right of carbon. And so from this bottom trend down here, I would expect phosphorus to have a higher ionization energy. On the flip side, carbon is above phosphorus. So from my up-down trend, I'd expect the opposite. And that means just like before, we can't tell with this comparison. Okay, so that's how we can use our periodic trends to predict and compare the properties of different elements based on their position on the periodic table. There's tons of other trends here, so these are just two of many. But once you get the basic process and you look up the trend for the other ones, those are pretty straightforward as well. Hey, hey.